The image is fine, the behavior is wrong. That is the quiet disaster of modern software. You ship the same container everywhere, and yet locally the database lives on localhost, while in the cloud it lives behind a service name you never baked into the binary. Rebuild the image for every host name, and you have turned configuration into a factory process. Forget to rebuild, and a perfectly healthy application talks to the wrong machine. Configuration is useful precisely because it changes. Change is also what can destabilize a running system. The question that opens this story is simple, and it is not a Kubernetes trivia question. How do you change an application's behavior without rebuilding the application itself? The answer the cluster offers is a small API object with an oversized job. Hold the settings that should never have lived inside the image in the first place. A config map stores non-sensitive configuration data in key value pairs, separate from application code. URLs, host names, feature flags, log levels, settings that differ between a laptop and a production cluster. It exists so the same image can travel, while the environment around it is allowed to disagree. You can feed that data three ways: as environment variables, as command line arguments, as mounted configuration files inside containers. Those three paths are not decoration, they are the whole delivery system. An example makes the stakes concrete. Database host equals localhost on your machine. Database host equals my-service in the cloud. Same binary, different truth. There is a hard note attached. Config maps are not secure. Sensitive material belongs in secrets, and they have a 1 megabyte size limit. For larger files, the cluster wants Kubernetes volumes, not a stuffed config map. Keep that ceiling in mind. It will return when people try to hide an entire application handbook inside a single object. Creation is where the story becomes operational. In Kubernetes, you can make a config map with qkubtl commands, the imperative path, or with a YAML manifest, the declarative path. Imperative is a spoken sentence, do this now. From literal values, the command is qkubtl create config map, a name, demo-config, then 3 from literal flags. Database host set to 172.138.0.1, debug mode set to 1, log level set to verbose. The cluster answers with a single confirmation, config map demo-config created. You can also create from a file, qkubtl create config map demo-config from file equals config.properties. The file's contents become keys. The object is born already populated. This is how a properties file on disk becomes cluster state instead of something tucked into an image layer. The name demo-config will follow us. It is the working example, a host, a debug switch, a log level. Small on purpose, small enough to inspect, small enough to break if you treat it carelessly. The declarative path writes the same truth as a document the cluster can apply again. You create a file, config.yaml, API version v1, kind config map, metadata with name demo-config, then data, database host quoted as 172.138.0.1, debug mode quoted as 1, log level quoted as verbose. Those quotes matter. The data field holds strings. Even a number is a string here. Then you apply it. kubectl apply -f config.yaml. The cluster may warn that a last applied configuration annotation is missing, then patch it. Then say config map demo-config configured. After that, you have an object named demo-config storing key value pairs, ready for pods. Imperative creation is a handshake. Declarative apply is a contract. The YAML can live in version control. The cluster can be told again and again, this is the intended state. That is why the document treats the manifest as more than a convenience. It is how configuration becomes reviewable, not just typed into a terminal at midnight. Once you can create the object, the document turns stern. Best practices are not etiquette. They are the rules that keep configuration from becoming a second source of outages. First, use config maps for non-sensitive data only. Do not store passwords, API keys, or other confidential information. Use secrets instead. Second, keep config maps small. They have a 1 megabyte size limit. Large files belong in volumes. Third, use immutable config maps when possible. Immutability prevents accidental changes and keeps configuration consistent. Fourth, name clearly and consistently. A name like dev-db-config tells you purpose and environment. Demo-config is a tutorial name. Production wants a name you can grep at 3 in the morning. Fifth, version your config maps. When updating, create a new object instead of mutating the old one, so running pods do not fight over a moving target. Sixth, mount carefully. File paths inside pods must not collide with files already in the container. Seventh, monitor updates. Pods do not automatically reload. Plan for restarts if the process only reads configuration at boot. Flexibility without those rules is just a faster way to be wrong everywhere. Where does this object actually live? Not on a laptop, not as a stray file beside the container. Config maps are stored as API objects in the cluster's etcd data store. They are managed by the Kubernetes API server. You access or modify them with Q-control or with the Kubernetes API itself. That sentence changes the psychology of configuration. A properties file on disk is private until someone copies it. An API object is cluster state. Anyone with the right tools can list it, describe it, or change it. Visibility is a feature until it is a leak. When you write YAML, the data field must be strings. If you need binary content, you use a different field, binary data. A sample object named binary-config holds text data as an ordinary string. This is a string value. Under binary data, a key called binary-file holds a base 64 encoded blob. Same config map, 2 rooms. Text in one, encoded bytes in the other. The encoding is not encryption, it is representation. Do not confuse those two words. We will need that distinction when secrets enter the story. Once configuration lives in the cluster, the next question is almost moral. Can you see what the cluster is actually using? Listing is the first instrument. kubectl get config maps. The table returns names, how many data keys, and age. In the example, demo-config shows 3 keys and is 19 minutes old. Beside it, cube-root-ca.crt, a cluster certificate config map, shows 1 key. Listing tells you objects exist. It does not tell you what they say. For that, you describe. kubectl describe config map, then the name. For demo-config, you see name, namespace default, empty labels, empty annotations. Then a data section. Database host, 172.138.0.1. Debug mode, 1. Log level, verbose. Binary data is empty. Events are none. Describe is the close-up. You confirm the stored pairs without guessing. If a pod is misbehaving, this is where you look before you blame the application. The object is small, readable, and sitting in default. That readability is the gift. It is also the hazard. Plain text is easy to audit. It is equally easy to overshare. Sometimes you do not want a human-readable describe dump. You want a machine to pluck one field. The document shows a JSON path. Kube control get config map, the name, output JSON path of data, then pipe to JQ. In the worked example, the name is demo-config. The printer returns a small object. Database host 172.138.0.1. Debug mode 1. Log level verbose. 3 keys. No metadata noise, no events, just the map. That extraction is how automation stays honest. A script can assert the host before a rollout. A human can paste the same command at 2 in the morning and see whether last week's apply actually landed. Notice the tutorial also mentions a name, test-config, in the pros, while the screenshot uses demo-config. The lesson is the pattern, not the nickname. Substitute the name you care about. JSON path is a spotlight. Describe is a wide shot. Get is a roster. Together, they answer a chapter question that operators forget until an incident. What is the cluster actually holding right now, not what we intended last Tuesday? Once you can see it, you can change it. And that is when the danger begins. An easy edit can reach every consumer of that object. Visibility without a delivery model is only half the story. The next chapter is how a pod actually drinks this water. Delivery begins as files. You must first have a config map. Then you mount it as a volume in the pod specification. The volumes field is the handshake between cluster object and container file system. The worked example is a pod named my-pod. Inside, a container named my-container, image my-image. Volume mounts names a volume ConfigMap-volume and sets mount path to /etc/configmap. Lower in the spec, volumes declares that same name, and under ConfigMap, name my-configmap. Watch the two names. The volume has a local nickname, ConfigMap-volume. The ConfigMap object has a cluster name, my-configmap. The mount path is a directory inside the container. Keys of the ConfigMap become files in that directory. After the mount, the process can list /etc/configmap and cat a file such as my-file.txt. Those shell lines are not theater. They are the moment configuration stops being an API object and becomes bytes on a path the application already knows how to open. This is why large configuration files prefer volumes. A file tree is a natural shape for settings. Environment variables are a poor place for a multi-line handbook. The document's later quiz even leans on this idea. Config maps are suitable for configuration files because they can be stored as volumes. Remember the mount careful rule. If /etc/configmap already existed in the image with different files, the mount can hide them. The path is a contract. Choose it the way you would choose a street address, unique, obvious, and not already occupied. There is a second delivery path that looks like files and behaves like a launch command. You mount the config map as a volume, then you pass a file from that volume as a command line argument. The application never has to hunt for a default path. The operator tells it at start exactly which file to read. The example pod is test-pod. The container is test-container. The image is a placeholder for your application image. The command is a small shell, /bin/sh-c, then your -app-binary, with a --config flag pointing at /mnt/test-config/config.properties. Volume mounts names config volume at mount path /mnt/test-config. The volumes block, continued on the next page of the source, ties that volume to a config map named test-config. Three facts locked together. A config map named test-config is defined with a key config.properties, holding the application configuration. The pod test-pod mounts that config map at /mnt/test-config. The container executes a command that includes that file path as an argument. The binary stays generic. The flag carries the environment. This is how you keep images portable without teaching every process to read Kubernetes APIs. The process thinks it received a file. The cluster thinks it projected an object. Both are right. The cost is indirection. If the mount is wrong, the command fails at start. If the key name does not match the file name you passed, the binary opens nothing. Names have to rhyme across YAML, volume, path, and flag. That rhyme is the whole craft. Flexibility is a rival of stability. The document introduces a third character, the immutable config map, read-only objects that cannot be modified once created. They exist when you want configuration not to drift, not to become inconsistent while the application runs. The workflow is deliberate. Create a config map with the immutable flag set to true. Once created, you cannot modify the data or the metadata. If you need new values, you create a new config map. Then you update pods to reference the new object. The YAML in the source places the flag under metadata annotations, immutable, quoted true, with a comment that says set the immutable flag to true. The object is named test-config. Under data, a key config.properties holds a multi-line block. Database URL, debug mode true, log level debug. You apply with kubectl apply-f test-config.yaml. After that, an edit is not a suggestion, it is a refusal. A terminal dump in the forest shows the failure in plain language. Field is immutable when immutable is set, forbidden. The cluster is not being polite. It is protecting the contract you asked for. By using immutable config maps, you help prevent inadvertent modifications that can compromise stability, and you keep configuration consistent and dependable. The hook is uncomfortable. Preventing edits does not automatically rewrite every running pod. Immutability locks the object. It does not teleport new values into old processes. That gap is the next chapter. If the object is not immutable, the cluster still lets you change it. The document names two doors. One is editing the YAML file and applying again. The other is kubectl edit config map. That command opens the live object so you can type changes in place. There is also a line the source writes as kubectl update config map with an example, my-config map from-literal key1 equals value 1, from-literal key 2 equals value 2. Treat that as the document's update example, a pair of new literals pushed onto a named object. Then the source splits the universe in two, and this split is the whole operational plot. Data mutation, Kubernetes applies modifications to the current config map object. It does not mint a brand new item. The existing one is altered in place. The modified configuration data is automatically sent toward pods that reference that object. Pod updates, when the config map is updated, pods that use config maps as environment variables or mount them as volumes are not automatically restarted. Until they are restarted or terminated, running pods continue under the previous configuration. Hear both sentences together. The object can move, the process may not. Mounted files may eventually show new bytes after the kubelet synchronizes. Environment variables are typically captured at container start. A process that read a host name into memory at boot will keep talking to the old host while the API object already shows the new one. Inspection can lie in a subtle way. Describe looks current. The running binary looks historical. That is why the best practice list said, monitor updates and plan restarts. The cluster will not parent you. It will store the new map and wait. Picture a timeline. At time 0, demo-config says the database host is 172.138.0.1. A pod started then, injecting that host as an environment variable, and another pod mounting the same keys as files. At time 1, someone edits the config map. The API object now says a new host. Data mutation has already happened. The map in etcd is new. The environment variable pod is still running. It will not notice. Its process table still holds the old string. Until that pod is restarted or recreated, it operates under the previous configuration. The volume pod is more subtle. The kubelet may project new files into the mount after a sync period. An application that rereads the file can see the change. An application that cached the file at boot will not. The source is blunt. Pods are not automatically restarted. This is the cost of decoupling image from config. You gained the right to change settings without a rebuild. You inherited the duty to decide when processes must be born again. Immutable objects force that decision into a new config map name and a pod spec change. Mutable objects let you edit in place and hope consumers catch up. Hope is not an operation strategy. The remaining question is not only when to restart, it is what must never live in this object at all. What must never go here? The comparison table is the document's last hard line. Purpose: a config map stores non-sensitive configuration data. A secret stores sensitive or confidential information. Data encryption: config map data is not encrypted. Secret data is encrypted. That single row should end a class of mistakes. Base 64 in binary data is not a lock. Plain text in describe is not a bug. It is the design. Use cases follow the same split. ConfigMaps store environment variables, configuration files, ordinary settings. Secrets store passwords, API keys, certificates. Access control. The table says config maps are accessible to all pods within the cluster, while secrets have restricted access based on RBAC policies. Kubernetes API. One object is type config map. The other is type secret. Visibility. Configurations are visible in plain text. Encrypted secret data is not visible in plain text. Usage. Config maps suit non-sensitive data that needs to be shared. Secrets suit sensitive data that requires encryption. Put a password in a config map and you have published it to every describe, every JSON path, every curious list. The image can stay still. The secret cannot live in the same drawer as the log level. That boundary is not optional hygiene. It is the difference between portable configuration and an incident report. Walk the same application through 2 rooms, because the table is easier to remember as a scene than as 7 rows. In the config map room, the lights are on. Database host, debug mode, log level, sit in data, printable, shareable, 1 megabyte or less. kubectl get, kubectl describe, JSON path, all of them speak the values out loud. Any pod that can mount or consume the object can read them. There is no encryption row that saves you. In the secrets room, the lights are lower. Passwords, API keys, certificates. Encrypted at rest according to the table. Restricted by RBAC. Not meant for the same casual describe and paste workflow you used on demo config. The API kind is secret, not config map. Mixing them is how a hostname tutorial becomes a credential leak. Notice how many of the best practices we're already pointing here. Non-sensitive data only. Keep objects small. Name them so a human can tell a database host map from a token. Version them so a leaked object can be replaced, not quietly edited. The table does not invent a new philosophy. It names the rival of config maps. Configuration wants to be seen. Secrets want to be scarce. If you only remember one sentence from this chapter, remember this. A config map is for settings you could print on a whiteboard. If you would not print it, it does not belong. 7 practices sound like a checklist. In a live cluster, they sound like incident reports. The first is the one teams break when they are tired. A config map is not a vault. A host name is configuration. A password is not. The moment a token lands in plain cluster state, every list, every describe, every backup of etcd can see it. The source is blunt. Keep confidential material out. If you need a key, you are already in the wrong object. Second, keep config maps small. There is a 1 megabyte ceiling. That is not an aesthetic preference. It is a practical bound on what you shove through the API. A sprawling properties dump belongs as a file on a volume, not as a stuffed key in cluster memory. Third, prefer immutable objects when you can. Mutability is convenient until an edit races a rollout. Fourth, names should tell a story. Dev database config is a name a human can find at 3 in the morning. Fifth, version configuration instead of silently mutating it. Create a new object, point the next pods at it, leave the old one as evidence. Sixth, mount paths must not collide with files the image already owns. A config map that overwrites an application's own settings file is a ghost in the machine. Seventh, monitor updates and plan restarts. Configuration that changes without a plan is just an unscheduled outage wearing a friendly name. Those 7 are not decoration. They are the difference between a reusable image and a cluster that quietly lies. Delivery is where configuration stops being a document and becomes a behavior. One path is a volume. You declare a volume whose source is a config map. You mount that volume into a container at a path. Each key becomes a file. The source walks a pod named my-pod, a container named my-container, a volume named configmap-volume, a mount path at etc configmap, and a config map named my-configmap. Inside the container, you list the directory. You cat a file. The application reads a path it already understands. That is why large configuration files belong here. A volume can present a file. A stuffed environment variable cannot gracefully become a 3,000-line config. The quiz on the last page of the source even leans on this idea. Config maps are useful for sizable files because you can store them as volumes, not because they are encrypted, not because they skip versioning. The other path is the command line. A pod named test pod runs a container that starts with an argument pointing at a mounted properties file. The command says, in effect, use this config path. The mount sits at mnt test-config. The config map is test-config. Name rhyme is a kindness. Name collision is a trap. 2 delivery doors, 1 object. Files for things that look like files, arguments for things the process expects on startup. Choose the door that matches how the program actually reads the world, because the cluster will not translate intent for you.